Okay, Assalamu alaikum and welcome back. This is now the last lecture in our DNA and Design Information Enigma subseries within the DNA and Design series. And this is really a more reflective lecture meant to acquaint us with some emerging topics and with a very vigorous debate about the nature and origin of information in DNA. A debate that we as um, religious people interested in science should be familiar with, and a debate that unfortunately, by and large, obviously there are exceptions, but by and large, we as Muslims are not really contributing to. And two of the main questions in this debate are, number one, can random processes produce information? So the information that we've seen contained in DNA, could this really have arisen by a random process? And I think our last several lectures have given a fairly convincing answer that no, it could not. However, the critics of intelligent design say that, well, we are just setting up a straw man to knock down, and that Darwinian evolution is not a random process. And so, can natural selection in Darwinian evolution produce a refined search so that I am not undergoing some random process to try to make giraffes with long necks, but that natural selection is refining that search by giving a survival advantage to those giraffes that have longer necks. Let me give us an example to maybe put things more in perspective. I don't know if when you were a child you sort of played a treasure hunt game where someone would hide something in a large area, perhaps in the whole house or in a large park, and now you're supposed to find that little treasure. And of course, if you search randomly through the house or through the park, that is a very low likelihood of success situation. However, if you have someone telling you, colder, warmer, hotter, I don't know if you've ever played that game. I used to love playing that game as a child, and my kids loved playing it when they were children. And we would hide something in a certain place, and if they got closer to that place, we'd say, you're getting warmer, you're getting warmer, you're getting hot, you're boiling. If they started to drift away, we'd say, oh no, now you're getting colder, oh, you're getting very cold, you're freezing. And those hints that we were giving are a an information input into their search so that it is no longer a random search, but really it is a refined search. And Darwinian evolutionists say that the survival advantage is basically giving a refined search, like nature saying to the giraffe, you're getting warmer, you're getting hot as its neck grows longer and longer by random mutations and variation. And so that hopefully summarizes some of the essence of the debate. And now let's get a little bit deeper into things. And I'd like to start doing that by acquainting our viewers who may not yet be acquainted with something very interesting in computer science known as genetic algorithms. For those of you who are acquainted with computer science and artificial intelligence and optimization techniques, you will already be very familiar with genetic algorithms, so please just bear with us. The idea of genetic algorithms is that it is a computer methodology that models itself after mutation and natural selection, after the pillars of evolution. So let's say, for example, I want to search for a target phrase, like me thinks it is like a weasel. That's a phrase from Hamlet, and it was actually used by the famous evolutionary biologist Richard Dawkins in one of his early computer programs to try to prove the point that Darwinian ideology can indeed produce information, that mutation and natural selection can lead to a refined, meaningful result. So the way this would work is you would begin with what is called a parent population. You would write a computer program that would begin with a lot of different strings of random letters. And then let's say you take two of these parents, parent A, parent 1, and parent 2. And you would have those parents, quote unquote, mate to mix their genetic information, because the random letters in the parent are sort of their genes or chromosome. And what you would do is have the computer program do a couple of different things. It would pick some chunk of genes like B, C, D, E from parent 1, and it would mix it into the genome of parent 2 and substitute it for A, D, B, E in parent 2. And by doing that, you have now created a child, an offspring of parent 1 and parent 2 that has some of the genetic information from parent 1 and some of the genetic information from parent 2. Then you introduce a mutation so that some of the genes of the offspring can be mutated. So whereas the offspring was supposed to have, from just the mixing of the genetic information of the parents, F, G, H, B, C, D, E, A, now we get a mutation and the H is mutated to an M and the A is mutated to an N. We just randomly have the computer select with a certain frequency some of these genes and mutate them. So now I have an offspring that has mixed genetic material plus the effects of a mutation. And from the entire parent population, which may be hundreds of parents, I generate hundreds of offspring with mutations. Then what I do is I select those offspring that are closest to my target phrase. So all of the offspring will have random letters, but some of them may have, for example, some of the letters in the right place to produce the phrase, me thinks it's like a weasel. Some of them may have an E in the second place. Some of them may have an L in the last place. Some of them may have both, etc. So I select that subset of offspring that is the fittest, that is closest to my target. Then I mate them, I introduce mutations into them, and I keep the process going at each generation, selecting the fittest, the fittest, the fittest. So this is basically a computer algorithm that is trying to mimic the principles of Darwinian evolution. And that's why this class of computer algorithms is known as genetic algorithms. And what we see when we run such a computer program is that if on the vertical axis you sort of look at the best score, 100% meaning that you've achieved the target phrase, and on the horizontal axis the number of generations it took you to do that, depending on the complexity of the problem, depending on the parameters that you select as you program the algorithm, such as the mutation rate and the so-called fitness function to cull the offspring into the most fit, you will eventually, and sometimes actually fairly quickly, converge to the desired solution. And very early on, Richard Dawkins used such a program to have it produce the phrase, me thinks it's like a weasel. And the claim was, see, Darwinian evolution can produce desired results. It can produce complex, meaningful information like genuine sentences, starting with random collections of letters which are meaningless through the process of mutation and natural selection. So in response to these claims that genetic algorithms can produce useful information, several people, in particular William Dembski, whose name has come up before, a mathematician, philosopher, and leading intelligent design proponent, has pointed to a couple of well-known theorems in computer science in the field of optimization known as the no free lunch theorems. And again, we can't get too technical in these lectures, but we also want to be acquainted with what is going on out there. And as you notice, these lectures have really not focused on Quran or Hadith, because I think we as Muslims, of course, need to study Quran and Hadith, but we also need to study the foundational sciences of our time, and then apply the principles of Quran to them, and in the reverse direction. For me, the study of science helps my understanding of the Quran and increases my wonder at the marvel of this creation. So I hope you forgive me for getting into this level of detail. But what the no free lunch theorems say is that if you have something like genetic algorithms that are searching for a target, that when you average their performance across all possible targets, they do no better than random search. Now, what does that mean? Basically, for our purposes, what it means is that if you look at the way the genetic algorithm that we talked about converged on the phrase "me thinks it's like a weasel," it was not doing a random search by just putting random letters together over and over and over and seeing, hey, did I get the phrase "me thinks it's like a weasel"? The search was refined over every generation. It was a directed search. Now, this refinement took information. Information had to be input into the system. A computer program had to be written that took parents, produced their initial genetics, had the parents mate, mixed their genetic material, caused mutations, and then had a fitness function that would select the fittest of the offspring, move them to the next generation, and repeat the process over and over. All of that is information being put into the system. And so the proponents of intelligent design have pointed to the no free lunch theorems, saying that basically what they show is that the improved performance over a genetic algorithm compared to a random search is exactly balanced by the amount of information I had to put in to create that genetic algorithm. And so I did not produce any new information. And from this sort of thinking, William Dembski in particular has coined a law, although others before him have used the same term, the law of conservation of information, that the amount of information that is put in to make a search more effective exactly balances the amount of effectiveness that I get. I can't get a free lunch. There's no one magical method that will all of a sudden start producing information. If I want some useful information out, I have to put useful information in, and it has to be the same amount of information in a sense. And so he has coined the term the law of conservation of information. If you're interested, you can look up the article that is on the slide. It's on the web, and get his take on why he thinks that random processes cannot produce any useful information. Now let's again try to bring it home with an example. And again, it's a detailed example, but I think it makes a useful point. And once again, I am assuming that those who have gotten this far in this series love science and love detail. They view it as a plus, not a minus. So let's say, for example, I want to calculate the square root of a number. I need this information. Well, I could do a blind random search. I have a target number that I want the square root. So for example, in this particular case, we're going to look at the number 125,348. Just a random number, a big number, where I'm sure that off the top of your head and off the top of my head, we don't know the square root. Now, I could start just picking random numbers and multiplying them together and see, do I get 125,348? That would be a very inefficient search and almost guaranteed to fail. But I can enhance the search. And there's a method called Newton's method for calculating square roots. And the way this method works is actually quite simple. Don't be daunted by the equation that you see on the top. The equation says start with the number whose square root you want. We're going to call that S. In this particular case, S is 125,348. Then start with any initial guess that you want. Just take a guess at what the square root might be. So start as if you're doing a random search. We're going to call that X sub n. I'm going to start with that guess, and what I'm going to do is I'm going to take S, the number whose square root I want, divide it by my random guess, add it to my random guess, and take the average. As simple as that. That procedure will give me a new random guess, and then I will repeat the exact same process over again. I'll take that new random guess, call it X sub n or X sub n plus 1, but I will simply divide my target number by that random guess and take the average of it with the random guess, make that my new random guess, and so on. So let's see this process in action. Let's say my first guess, which we'll call X sub 0, is 600. So I have 125,348. I want to calculate its square root to 6 significant figures. And of course, there are some details in the algorithm, like when do we stop and so on, that I'm glossing over, but I just want to show you the basic method. So what we're going to do is the first time out, we're going to, and before I go on, please look again at the top equation. You know that a square root is that number multiplied by itself produces my target number. Like 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. So if 16 is my number, then 4 is its square root, because 4 multiplied by itself gives me 16. So let's say my target, let's say that X sub n is actually the square root. It is the real square root. So what happens when I run my algorithm? Well, I divide S by X sub n. What will that produce? That will produce X sub n. Why? Because if X sub n is the real square root, then X sub n times X sub n equals S. So if I divide S by X sub n, I get X sub n. I add that to X sub n, I get 2X sub n, I multiply it by a half, I get X sub n. So when I reach the real square root, the algorithm has fully converged. I no longer have any changes. My next guess is the same as my last guess, and I've reached the square root. And there are stopping rules that when you get close enough, when the change is very minimal, you've reached close enough to your real square root. So now let's watch it in action. I start off with my guess as 600, and what I'm going to do is divide 125,348 by 600 and average that with 600. Add it to 600 and multiply by a half, I get 404. 404 now becomes my next guess. It replaces x sub n, so I divide 125,000 by 125,348 by 404.457, average that with 404.457, and I'll get a new guess, which is 357.187. I'll repeat the process again. Very soon, with only 5 iterations, I reach 354.045, which has not changed in 3 significant figures after the decimal point from my last guess. And so I say, okay, I'm now close enough to the square root. So instead of randomly guessing numbers, I probably would never have guessed 354.045. We used an algorithm to refine the search. Now, the argument of William Dembski is that the amount of information I put into the program up front to find Newton's method and to program the computer is equivalent to the information I get out the back end. And I very much agree with this sort of thinking. Unfortunately, we don't have a way to precisely measure how much information is in this sort of algorithm. But it makes tremendous sense to me that what we have done here is very similar to, for example, the steam engine that used to run early trains, where you dump coal into the furnace and you turn that into heat and steam, and then I basically convert that chemical energy stored in coal to heat energy, then to mechanical energy to move the train. So I take one type of information, which is the brain power, if you will, to figure out the algorithm, and I convert it to another type of information to give me the square root of 125,348. Now that's a piece of new information. I didn't know that square root before. On the other hand, I had to put in a certain sort of information that in some sense got converted over to a new kind of information, which is the square root. So I do agree that in some sense there is a law of conservation of information. Now, William Dembski's point of view is that this conservation of information shows why Darwinian evolution cannot create biological information. And that's really where the debate comes in, is that the intelligent design community, or at least part of the intelligent design community, says that this no free lunch theorem can be used to deduce a law called the law of conservation of information, and that from there we can then deduce that Darwinian evolution cannot produce biological information, that if natural selection is a refined search, that means that there's already information stored into the environment that is helping refine the search. The information that says, yes, you are more fit to survive than another organism, and keeps refining your characteristics, like the neck of giraffe, the giraffe growing longer and longer. That is sort of information built into the system. It is, in essence, the Newton's algorithm of nature that is producing this. Of course, the opponents of this point of view are saying, and you can look at the number 1 point in the response, that the no free lunch theorems do not apply to biological evolution. And they look at the mathematical intricacies of the no free lunch theorems and the idea of fitness functions. And they say, no, evolution is not trying to produce some very specific sequence like me thinks it's like a weasel. It's trying to produce any meaningful sentence of any sort. And so if we were just focused on producing an organism with a long neck, and that's all we're searching for, yes, perhaps, but we're focused, for example, think of wolves that hunt deer. Evolution, or the law of survival of the fittest, is not necessarily focused on the deer with the longest legs. Any sort of solution that will make some of the deer more fit to survive against the wolves, whether it is lighter bones so they can run faster, or stronger muscles, or longer legs, or the exact same body type but with a stronger cardiovascular system, or more efficient energy metabolism so that they can then run faster. Any of those will work, and they're saying that in this undirected scenario, the no free lunch theorems do not apply. Now, my claim is that there's no definite answer at this point, but this is what we should be talking about. As Muslims, we should acquaint ourselves with this debate, and whoever of us can contribute meaningfully should contribute. So I think that both sides have overstretched their claims a little bit. As I'm taping this, it is 1 year into the COVID epidemic, and all of the news now is that there are new virus variants. There's a variant in South Africa, there's a variant in the United Kingdom, there's a new variant in California, and the UK variant is supposed to be much more infectious, therefore much more adept at reproducing itself, and is predicted to actually become the dominant variant in the United States in a matter of just a couple of months. So here we see that natural selection, because one virus is more fit to survive, it can reproduce better, it will become dominant. And this pressure of random mutations in the virus and natural selection has produced an entirely new organism. So new biological information has been produced. And we see this with resistance to antibiotics and bacteria all the time in medicine. And that's why we're advised not to take antibiotics willy-nilly, because we don't want to produce resistant bacteria. If bacteria are exposed to antibiotics, random mutations can arise in their genetic code to make them resistant to the antibiotics, and then those bacteria that are will survive better and they will become the dominant strain. Then we produce a new antibiotic and the process starts all over again. So clearly, random mutations and natural selection can produce new information. That's why I think that Dembski has overstretched his argument. However, let's be very clear about something, that for natural selection and random mutation to work, I need to begin with living, reproducing organisms. So let's grant for a moment that once I have that first living, reproducing cell, that random mutations and natural selection can produce the entire diversity of life. I myself do not believe that, but let's take that as a given. Our question here, what we've been dealing with in this lecture series, is a more basic question. Even the simplest living cell is a very, very complex, integrated informational network. How did the information in the DNA to produce the first living, functioning organism arise? In that case, there is no natural selection. Now, a lot of the science community has tried to sort of gloss something by us under the rubric of prebiotic evolution, that the same process that takes a single-celled organism into a complex thing like a human being can take primordial chemicals in the chemical soup and turn them into a living cell. But these are totally different processes, and many biologists, not from a religious point of view, have objected, saying that this notion of prebiotic evolution is nonsensical, that it presupposes the problem it's trying to solve. Because for the mechanism of natural selection to work, you need a living, reproducing cell to begin with. And so I think that Dembski is right in that in the prebiotic environment, we are indeed doing a random search. We do not have natural selection to be telling us warmer, colder, hotter, to be injecting information into the system. it is truly at that point a random search. And in that circumstance, I do think that he is entirely correct that there would be a law of conservation of information, that that you would be doing no better than a random search. And we've already seen that a random search cannot produce the informational content in DNA. This was very nicely expressed by a scientist named Hugo de Vries. And I'm just bringing it in because it's such a beautiful quote. And he wrote this book way back in 1905. And he said, natural selection can explain the survival of the fittest, but it cannot explain the arrival of the fittest. And I thought it was such an eloquent quote because it so pithily summarizes what we've just been saying. Even if natural selection can explain the increasing complexity of life, it cannot explain the origin of first life. And our focus in this lecture series on the information content of DNA is about where did this very, very primitive code that essentially coexisted with first life get that huge information bolus to produce something as complex as a living cell. Whichever way that debate shakes out, one thing is clear. Information is becoming more and more central in the world of physics. And I wanted to give you some quotes from Max Tegmark, who is professor of physics at MIT, interested in quantum mechanics, interested in its connection to information. And he recently headed up a symposium about the physics of information, because we've always thought of physics as the study of matter and energy and how they interact. But a new view is now springing up in the world of physics that it's matter, energy, and information, that information is just as central, and that maybe those who say that there is a law of conservation of information are indeed correct. So I just want us to read together these quotes from Max Tegmark's interview about the physics of information. And the interview itself, you see the website down below where you can access it. And he said, we used to think it, meaning information, was utterly unimportant. We used to think information was just some sort of sideshow that had very little to do with physics. And then remarkably, information has started to crop up in area after area of physics at a very fundamental level. Then he comes back later and says, it makes me wonder if one of my greatest heroes, John Archibald Wheeler, he was one of the truly great physicists of the 20th century, professor at Princeton for a long time, was right when he talked about it from bit. That was a phrase that John Archibald Wheeler coined, and what he was getting at here is that there is a fundamental divide in worldviews. Some people think that matter came first, then mind. What does that mean? It means we have random bits of matter that were created in the Big Bang, and somehow those random bits of matter congeal in a complex enough fashion to produce consciousness and mind, and then information from those minds. The other worldview is that no, information came first. Mind came first, and mind produced matter. That what we see had to have been produced by an intelligence. And John Archibald Wheeler was not a conventionally religious man, as far as I am aware, but his view was that it came from bit, that information comes first, and then it produces everything else, so that information needs to be looked at as a fundamental component of the building blocks of the universe. And then Tegmark goes on to say, maybe information is not just some sort of coincidental little thing, but maybe information is really, truly fundamental, and maybe it is more fundamental than matter and energy and space, so that maybe we can understand how these things that we thought were the building blocks of physics emerged from information, or at least unify everything with information. So I thought that it is important for us as theists, as religious people, to understand, as we're talking about the information content of DNA and where this could have come from, that the entire world of physics is on the cusp of a major shift, a major paradigm shift, where we now start to see information as the fundamental component and everything else comes from that. And again, you can, I'm sure, see the theistic implications of that shift. Now, I'd finally like to end this sub-series of lectures on the information enigma with something that I hope you find quite amazing. This is something from the University of Texas Science News, their science and technology section. You can see the date, it's July 14, 2020. So you can see that we are right at the cutting edge. We have talked about the information stored in DNA and how amazing that is. We've talked about the DNA code and how it's an optimal code and how amazing that is. We have not yet talked about DNA as an information storage mechanism. So let us not confuse the information with the storage mechanism. So for example, I could have a thumb drive, that's an information storage mechanism, and then I can store any sort of information on it. I can store amazing information, like the works of Shakespeare, or I can store nonsense, like random strings of digits or random letters or just low grade, writing. So what we want to talk about now, very, very briefly, is the new sort of arena in science that is looking at the information storage mechanism. So for example, if you're old enough like me, we know that thumb drives are a fairly recent thing. Before that, we used to use hard disks. Before that, we used to use floppy disks. Before that, people stored things on these big things that were like a record, that were a huge laser disk. So the information storage mechanism, regardless of the information stored on it, has been getting better and better and better. At actually an amazing rate. Scientists are now discovering that as an information storage mechanism, DNA is utterly astounding, and they are beginning to engineer DNA to store information. So of course, DNA stores our genetic information, but if you can use the same code to code something else, turn the code, instead of coding for amino acids, to code for words or to code for numbers or to code for something else. And if I wanted to now use this information storage mechanism, look at what the UT News is saying. That DNA is about 5 million times more efficient than current computer storage methods, than current storage methods. Put another way, a 1 milliliter droplet of DNA could store the same amount of information as 2 Walmarts full of data servers. And DNA doesn't require permanent cooling and hard disks that are prone to mechanical failures. So I thought that this is a very fitting tidbit to end on our lecture series about the information enigma in DNA, that not only is the information content utterly amazing, and not only is the code to store that content utterly amazing, but the storage mechanism itself, the quote-unquote thumb drive that is DNA and chromosomes, is 5 million times more efficient than our best current storage devices. And the question becomes, how could this have arisen through a blind, random, prebiotic search without the benefit of any natural selection, and of course without the time for natural selection to act, because we've already covered how DNA is essentially as old as life itself. I will leave that as a rhetorical question, which is what I mean it to be. I hope you are enjoying this lecture series so far. We still have a couple more topics to cover, but we have now finished the information enigma portion of our DNA and design series. Take care. Assalamu alaikum. God bless.